Good morning, Calc 2 students. I want to add a little bit to the videos I posted about polar coordinates. In particular, I want to talk a little bit more than the calculus professor did about graphing polar functions. And so I'm going to do, I think, 3 examples. Some of these will be very much like things you'll be expected to do on the final exam. I'll be more specific a little bit later. So I just want to think about it a little bit. I'm going to start with the real simple one. Algebraically, r equals theta. Super simple function. In rectangular coordinates, y equals x, we get a line, a simple line. Here, it's a little more interesting. R is a function of theta, and so let's just plot a few points. When theta equals 0, so does r. So the origin, sometimes called the pole in polar coordinates, is on the graph. Notice I've set up 3 concentric, almost concentric circles here. The graph situation presented in this manner is called polar graph paper, and it's really helpful. We can assign these circles to a value, an r value, and I think for this problem, just using unit increases. So r equals 1 would be here, r equals 2 there, and so on. If I had a different function, I might decide, the distances between the circles need to be different. But for this one, I think 1, 2, and 3 will work. Now, when theta gets up to pi over 2, r is pi over 2. Well, pi over 2, 3.14 divided by 2 is about 1.57. So I'm at pi over 2. Here's 1, and we need to go up, and this is 2 units away. R is 1 here, R is 2 there. Well, we need to be at 1.57, just a little tiny bit over halfway in between. And as we go from here to there, theta goes from 0 to pi over 2. R gradually increases. Well, R increasing means it gets further away from the origin. And so we get a graph that looks sort of like that. Gradually further away from the origin. By the time theta gets over to here, of course, this angle is pi. And so r is at 3.14 pi. It's a little bit outside this outer circle, just a little tiny bit. We head over there. And as theta keeps on increasing, r just gets further and further away. And so what we get is this big spiral. As theta goes around and around, r just follows it, getting further and further away from the origin. So, an ugly picture, at least beyond this point, but you get the ideas. So, super simple algebra generate very interesting curves that we have never seen really in rectangular coordinates. And that's part of the power and the beauty of polar coordinates. They let us easily talk about completely different things. So that's the first example. Here is the second one. Let me set it up for you. I'll just draw the polar graph again. So concentric circles, it's easy to draw the circles first and then put the axes. At least it's easier for me. Not quite as pretty as the last one, but you get the idea. And I think this example also, we can just use a unit distance between the circles. So not super accurate, but good enough for what we're going to do. Now I'm going to graph the function 1 plus sine theta. The polar function 1 plus sine theta. You should know your calculators have a polar graphing mode available to you. And as you're working through these examples with me and then on your own, you should check things out. Convert your calculator to graph polar functions just as a confirmation. The kind of analysis that I'm going to do here for this function is what I'm going to ask you to do on the final exam. So pay attention. It should also be on the homework as well. So what I like to do for functions like this is analyze them by quadrant. The sine function is pretty predictable if I restrict it to one quadrant. So I'm going to make a table of values. So let's say the first column, we're going to put the quadrant, and the second column, we're going to put the theta values in that quadrant, and then we're going to figure out what sine does in that quadrant. And finally, we're going to figure out what the function does. I'll just call it R there. So quadrant 1, theta goes from 0 to pi over 2. And the sine goes from 0 to 1. Okay, should be nice and easy there. And R, well, R is 1 more than the sine. So when sine is 0, R is 1. When sine is 1, R is 2. So we start here. We end up there. R goes from 1 at theta equals 0 up to 2 at theta equals pi over 2. And kind of like the spiral, it just increases. But I want to calculate 1 point because it's easy to calculate and it will help us. It will give us a target to shoot for as we make our trip from there to there. And that is the angle in the first quadrant where sine is equal to 1/2. Happens to be pi over 6. So if theta is pi over 6, R equals 1 plus 1/2. I picked that specifically because it has a simple value, 1/2. And if you add those up, we get 3/2. So at pi over 6, which is 30 degrees, about right there, R is 1.5. So we've made it half of the way between 1 and 2. So I'm just going to draw that point. It will help me draw a better graph. I think I'll graph it in red. Something like that. All right, quadrant 2. Theta goes from pi over 2 to pi. Sine goes from 1 back to 0, just retraces its steps. Back to 0. And therefore, R goes from 2 back to 1. So basically, I don't think we need to do any calculations. It just retraces, although we're in quadrant 2 now. So this would be the angle 5 pi over 6. And we have this halfway point. And then the graph just, we're headed back to there, back to 1. And we'll just do something like that. Quadrant 3. Theta goes from pi to 3 pi over 2. And sine goes from 0 to -1. R left off at 1, that's where we'll pick up here. And then 1 plus -1 is 0. So it ends up actually back at the pole, at the origin. And again, there's a point in this angle, in this quadrant, and there's an angle where we can calculate R real easily. It would be 7 pi over 6. The sine would be -1/2 because we're in the third quadrant. So 7 pi over 6, R is equal to 1 minus 1/2. So we made it half of the way back. So here's R equals 1, there's R equals 0, halfway between. Right there, grab my red pin. And so we're going to hit that point and then come back. And then, of course, we're going to just retrace it in quadrant 4. So there's our target point. And we end up with a beautiful graph like that. Some people look at the shape of that and they call it a cardioid. And in fact, we could be a little more systematic and look at all of the functions whose graph are cardioids. And we're not going to be that scientific here. But I want us to understand the process. Notice I didn't write the details for quadrant 4 because we're just going to retrace, just like we did in quadrant 2. We're going to retrace what we did in quadrant 3. Okay, then like I said, a cardioid there. I don't know, you spell it like that? Maybe there's only one eye there. Cardioid, there we go. If you're into sound production, then you've heard of things called cardioid microphones, and those are ones that who are efficient at picking up sound. I believe, I'm not an expert, but I believe the microphone would be situated right there, and then it would pick up sound in the shape roughly corresponding to a cardioid. So, you know, the graph maybe has some applications. How does it connect to polar? I'm not sure. We'll trust the audio technicians to work on those details. All right, I said I wanted to do 3 examples. There's a second one, the lesson here, and it will also be true on the next one as we analyze by quadrant. Because the sign, you know, it only goes one direction in a quadrant. It either goes from 0 to 1, back to 0, down to -1, real easy to describe. So the third example I want to do is 2 cosine theta plus 1. Let me set up my polar graph over here. I'm going to make the graph a little bigger. I'll make my concentric circles a little further apart. Cosine goes from -1 to 1. So when cosine is at its biggest value, r is equal to 3, 2 plus 1, and its smallest value is actually negative. Interesting, negative. So I know I need to go up to 3. R cannot get any bigger than 3. The graph is wholly contained inside. I'll use the same unit system, 1, 2, and 3. All right. Again, we're going to analyze quadrant by quadrant. So the same table of values. So we have q theta, this time cosine theta, and then finally r. So quadrant 1, theta goes from 0 to pi over 2. Cosine goes from 1 to 0. R goes from 3, if cosine is 1, 2 plus 1. And cosine is 0, it goes down to 1. So we start at 3, we end up at 1. 3 units away. At pi over 2, we're 1 unit away. And again, there's an easy angle that we know. For cosine, it happens to be pi over 3. So something like this. And if theta equals pi over 3, the cosine is 1/2. So you can see 1/2 times 2, we get r equals 2. So we're at that point right there. 2 units away. And again, I'll draw my graph in red. Start at 3, we gradually get closer to the pole, ending up exactly right there. Quadrant 2. Pi over 2 to pi. Cosine goes from 0 to -1, and therefore r goes from 1, if cosine is 0, to -1. Interesting. So in quadrant 2, the function goes from positive to negative. If you watched the previous videos, and especially the exercises that the calculus professor works out, then you know that when r turns negative, it means we measure in 180 degrees pi radians opposite. Okay, so we'll do that in just a minute. And I think it's easy to believe if r starts at 1 in quadrant 2, ends negative, -1, then somewhere in quadrant 2, it passes through the origin, through the pole. And I would like to find out where that happens. So, got some space I can use here. It happens when r is 0. That's when the graph is at the pole. So solve for cosine, we get negative. Subtract 1, divide by 2. And the cosine is negative in quadrants 3 and 4. I'm sorry, 2 and 3. So there are 2 angles, one in quadrant 2, one in quadrant 3, where r takes on the value 0. Of course, we're focusing right now on the one in quadrant 2. And it's going to be 2 pi over 3. It's equal to 1/2 at pi over 3. And so we'll take that same angle in quadrant 2, which that is same angle, pi over 3 here, pi over 3, sorry, pi over 6, pi over 3 here, pi over 3 there. So this is 2 pi over 3. And it passes through the pole. And it ends up, so when theta is equal to pi, as soon as it passes through the pole at this angle, 2 pi over 3, it's negative. So we start in this region here, we shoot back 180 degrees opposite into quadrant 4, and we end up over there. So if we sketch all of that information, we keep zipping into the pole, we pass through it, and we end up out there. So when theta equals pi, r equals -1. Here's our angle pi, and we go backwards opposite because r becomes negative. Okay, due to the symmetry of the cosine function, I think it's easy to believe that it's just going to retrace its steps. Sorry. And we go there, and we get the rest of it, which looks sort of like this. Beautiful. That guy has a name also. I think the name of it, and again, you have to memorize this. I think that it's called a limacone, which in French has a little curly on that C. I think limacone is French for snail, and maybe someone looked at that and thought they saw a snail-looking thing in there. Anyway, that's how we do it, quadrant by quadrant. We could talk about lots and lots of examples, but hopefully you get the idea. I will say we are really fortunate that when we solve for cosine, we got a half negative, but half is super important to graph it by hand because we know the angles where cosine takes on plus or minus a half. If we'd gotten a third here, like certainly that's a reasonable value, but we don't know any angle whose cosine is 1/3, you know, we'd have to use our calculators. Maybe that's not such a bad thing, but it's a true thing. So this was especially chosen with the 2 and the 1 over here, our original function, so that we could do the work using what we know. It's like I erased something there. I'll just cover it up. All the details are over here. All right, so there you go. You should have some Pearson homework that resembles what we have done here.